A junior engineer recently received a bill for $30,000 from AWS Bedrock. This was not a case of bad code or a simple typo. It was a runaway agent that burned through resources in an invisible loop. The real story is not about user error, but about a fundamental architectural flaw where inference hardware operates independently from cost-gating logic. By the end of this video, you will understand exactly why standard safety controls failed and how to design systems that prevent this specific type of catastrophic billing event. Consider the incident involving the AWS Bedrock agent core. A user triggered a self-sustaining loop that cost $30,000. The root cause was a failed stop hook for the Claude Code agent. When the agent encountered an error, it did not stop. Instead, the error output was fed back as a new prompt, creating an infinite cycle. This happened because the control plane marked the session as terminated while the underlying container continued burning uncapped resources. The hardware kept running long after the software thought it had stopped. This reveals a critical decoupling in the architecture. Inference hardware, specifically the microVMs running the models, operates with what feels like infinite resource availability. Meanwhile, the cost-gating logic remains passive, only triggering billing events after the damage is done. The system treats AI agents as stateless, ephemeral compute rather than stateful, controllable workloads. This design removes the engineer's ability to intervene during a runaway loop because there is no API to list active runtime sessions or force terminate microVMs. The absence of these APIs is the smoking gun. Operators faced a deadlock where the looping agent wrote to persistent volumes, preventing backup completion and blocking any attempt to shut down the container. Standard termination commands failed completely because the control plane and the compute layer were out of sync. The only workaround available was revoking IAM permissions. This was a blunt instrument that disrupted all active sessions, proving the lack of granular kill switches for specific runaway processes. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. You might think this is just a rare bug that could happen to anyone. But the pattern suggests a deeper issue with how we build serverless AI environments. Relying on application-level logic like stop hooks for safety is a single point of failure. The infrastructure layer lacks the native capability to enforce hard limits on active sessions regardless of the application state. When the application logic fails, the infrastructure does not step in to save the day. It just keeps billing you for the compute time. This failure mode demonstrates that the primary risk is no longer just code correctness or model accuracy. The new critical risk is the lack of infrastructure-level observability and emergency kill switches for AI workloads that scale autonomously. Without visibility into active sessions, you cannot know if a loop is running until the bill arrives. The system assumes that if the control plane says it is stopped, it is stopped. But the hardware does not care about the control plane status. It only cares about the power being drawn and the tokens being processed. The specific mechanism of the failure was a circuit breaker that never tripped. A transient API error was treated as a signal to retry, which generated more tokens, which triggered more errors. This turned a momentary glitch into a self-sustaining infinite loop that bypassed standard timeout protections. The system had no way to say stop. It just kept going, burning through the uncapped resources of the microVM. This incident highlights a career-critical shift for data engineers. You are no longer just writing code that runs on a server. You are designing systems that interact with autonomous agents that can scale without your direct intervention. The traditional safety nets of timeouts and error handling are insufficient when the underlying infrastructure is decoupled from the billing logic. You need a new approach that treats safety as a hardware-level constraint, not just a software feature. The lack of an API to list active sessions means you are flying blind. You cannot audit what is running. You cannot see the loop forming. You cannot force a shutdown of a specific microVM without affecting everything else. This opacity is what allows the $30,000 bill to accumulate silently in the background. The system is designed to be invisible, which is great for scaling but terrible for cost control when something goes wrong. We must also consider the implications of this design for future development. If the platform treats AI agents as stateless, then any stateful behavior like writing to persistent volumes becomes a point of failure. The agent writes to a volume, the volume fills up, the backup fails, and the shutdown command hangs. This creates a feedback loop that the infrastructure cannot resolve on its own. The only way out is to break the connection entirely, which is what the IAM revocation did. The singular nature of this reported $30,000 incident presents a knowledge gap. Without broader adoption data or benchmark results quantifying the frequency of such decoupling events, we must be careful not to overgeneralize. However, the structural issues identified here are not unique to this one case. The absence of granular control and the decoupling of compute from billing logic are systemic features of the current serverless AI architecture. For you as a junior engineer, this means your role is evolving. You are now responsible for the financial safety of your infrastructure as much as its functional correctness. You need to build in circuit breakers that operate at the infrastructure level, not just the application level. You need to assume that the control plane can lie to you about the state of your resources. You need to design systems that can be killed from the outside, regardless of what the application is doing. The lesson here is clear. The gap between understanding model latency and understanding the underlying hardware pricing model creates infinite scaling risks. These risks lead to catastrophic, unexpected bills when the decoupling between compute and billing logic is exposed. The $30,000 bill was not a mistake. It was the inevitable result of a system designed without the necessary safeguards for autonomous, stateful AI agents. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.